Okay, this is going to be our second video in our work and energy module. We're just going to be moving on with more ideas in work and energy here. Okay, so we're going to start off by talking about kinetic energy and the work energy theorem. We're then later going to derive the work energy theorem and do a number of examples where we make use of this work energy theorem. Okay, so to start off with, another way to think about work is in the context of energy transfer. So we can think about work as being the transfer of energy from the system doing the work to the system having the work done on it. And so this kind of brings up some questions about, well, what is this energy? Where does it go? Where is it stored? If we're talking about energy being transferred from one system to another, where is this energy stored when it's transferred into this second system, and so forth? So we have a bit of an example that I've kind of just talked about here briefly. If we think about our lawnmower example from last time, where we're pushing the lawnmower on flat ground. Well, the energy there isn't transferred anywhere. The energy is dissipated, right? So we have no acceleration as we're pushing the lawnmower. The lawnmower is being pushed along on flat ground at constant velocity. So all the work that we're doing is basically being dissipated in the form of friction. It's being dissipated in the form of heat and sound from that friction, right? Let's say we think of another example from our last video where we talked about the briefcase being carried up a flight of stairs. In that case, the energy is being stored in the briefcase Earth system in the form of gravitational potential energy. And we're going to talk more about these ideas. First we're going to talk more about gravitational potential energy, and we're also going to talk more about this idea of storing energy in different systems, but we'll save that for a little bit later. For now, we're going to move on and sort of derive what's called the work energy theorem, and from that we're going to sort of see the connection between energy, a specific type of energy, and work. So we're going to see the connection between kinetic energy and work. Okay, so we've seen in our first video on in this module that so maybe first, we've seen this equation in our first video in this module, but even before that, we've seen that forces can cause accelerations, right? Like from Newton's second law, we saw this, right? That forces cause accelerations, or if there is an acceleration, you should expect that there will be a force, right? But we also want to point out the fact that so jumping back to what we looked at last video, we sort of came up with this idea that the work is equal to the force applied. The work done on a system is equal to the force applied to the system times the displacement experienced by the system times the cosine of the angle between them, right? But we also want to consider the fact that this is true for net force as well. So we can look at any one individual force, and we can get the work done by that force. But we can also look at the net force applied to a system. So we can look at all the forces put together applied to that system, and then from that we can get the net work done on that system. So we're going to find that it's sometimes useful or necessary to look at the work done by a specific force, and other times we're only really interested in the sort of net force done on the entire system. And because of the way these things work, we're able to do that. We can isolate the work done by a single force, or we can isolate the total work done on a system, and we're going to see an example of that here in a little bit. But before we do that, let's get on to the derivation of the work energy theorem. We're going to derive the work energy theorem here in a special case for just a 1D system, but this derivation sort of applies very generally. This work energy theorem is applicable in a wide variety of systems. Okay, so here we go. Let's start off by imagining a box on a smooth surface. So a smooth surface, not too much friction on it. In the following setup here. So we have this setup down here. We have some applied force to the box. Okay, there's some force of friction opposing the motion of the box, and we have the box being displaced. This is the displacement vector of the box. So the box is being displaced in this direction down this surface, okay? We also have our normal force as usual, and we have the force of gravity down here pulling down, right? So if we were to take a look at this, and I'm not going to write out the full Newton's second law here, but if we were to take a look at this, we've done this a number of times. In the vertical direction, we're going to find that because there's no acceleration in the vertical direction, we find that the force of gravity, or our weight, our W, is equal to n here, right? In magnitude, at least, like they're opposite in direction, but we've seen that they're equal in magnitude, right? So there's no acceleration in the vertical direction. Let's take a look at what's happening in the horizontal direction, though. So if we focus on this direction, we see that our net force is going to be the applied force that we have in the positive direction, and the force of friction operating opposite to our applied force, right? Like resisting our displacement here. So if we take a look at this system, we're going to see that the angle. So we have our applied force like this and our displacement like this, right? I'm just moving these from over here, right? So if we look at that, we see that the angle between our applied force and our displacement is 0 degrees. They're pointing in the same direction, right? So if they're pointing in the same direction, that means that theta is 0. And if theta is 0, that means that the cosine of theta must be 1, right? And because that's true, we can then simplify this expression, because our cosine of theta goes to 1, and it becomes this expression here, right? So that's good. That's going to be one thing that we're going to want to do. We can also then use Newton's second law, which tells us that the net force is equal to the mass times the acceleration. Sorry, I had to mute myself there for a second. So yeah, we can use Newton's second law which tells us that the force is equal to the mass times acceleration. And if we substitute in this expression into this expression over here, we end up generating what I have in the next line here, our expression, our equation number 4, right? So the net work is equal to the mass times the acceleration times the displacement. But we can also rewrite our displacement in terms of our coordinates, right? So if our displacement, if we simply think of our starting point here as x naught and our ending point out here as x, then we can very easily rewrite our displacement in terms of x and x naught. So our final position and our initial position, just by doing this, right? And if we do that and we make the substitution into what I have labeled as equation 4 here, we end up with equation 5. And now, if we remember from our first module where we did all of our work on kinematics, we have an expression that looks like this, right? This is telling us that our final velocity is equal to our final velocity squared is equal to our initial velocity squared plus twice the acceleration times our displacement here. And our displacement is just our initial position minus our final position minus our initial position. So let's take this equation and isolate just this term here, the acceleration times our displacement. If we do that, we end up with this expression here, and note that we have these terms, this acceleration times our final position minus our initial position in the equation that we're trying to work with here. So let's make this replacement. Let's replace our acceleration times our displacement with what we have on the right over here, this final velocity squared minus initial velocity squared over 2. If we do that, we're going to end up with this expression down here. And then simply by cleaning oh, and I've forgotten. I see that so I forgot to put an m in here. There should be an m in here because you can see from up here there is still this m here as we make this replacement, right? So that's a little bit of a boo-boo there, but I will just rewrite that in there. So assume there's an m here, and then if we clean this up, we can see that that we're going to end up with the boxed equation that we have here. And this boxed equation, this is what we call the work energy theorem. And so what is it sort of telling us? Well, before we get into what it's telling us, let's name some of these terms. Okay, so we call this collection of variables, this half mv squared, as I have a little discussion about it here. We call this collection of variables our kinetic energy, and we sometimes relabel that as Ke. So that's our kinetic energy, a half mv squared. So the first term that we see here, this is our final kinetic energy, right? This is our kinetic energy at our V final when V is at the time that we're looking at, okay? And this other term, the second term here, where our velocity is our initial velocity, we call this our initial kinetic energy. So we have our final kinetic energy here and our initial kinetic energy here. And so if we rewrite this as our final kinetic energy, so kinetic energy or kinetic energy final, however you want to write it, and this is our initial kinetic energy 0 or kinetic energy initial, we can then write the change in kinetic energy as follows here. We have our final kinetic energy minus our initial kinetic energy, and this gives us another way, a sort of even cleaner way of writing our work energy theorem, and we have that down here. So we have the net work done on the system is equal to the change in kinetic energy, okay? And so when we think of kinetic energy, we want to be thinking of the energy of motion, right? So what is kinetic energy? Well, kinetic energy, again, is a half mv squared, right? So it scales with mass linearly, and it scales with a square of velocity. So this is really the energy that we have in the motion in the system. As velocity goes up, this thing goes up as a square of velocity, right? So you really always want to be thinking of this as the energy of motion, or the kinetic energy, okay? So I'm going to clean that up a little bit. And so what is the work energy theorem really telling us? Well, the work energy theorem is telling us that the work that we do on the system, the net work done on the system, is equal to the change in the kinetic energy, the change in the energy of motion in the system. So this is something we really want to keep in mind. And the equations that we want to keep in mind are this equation over here that I have boxed, and I probably should have boxed this one. This is one that we also want to keep in mind. And you also want to remember what kinetic energy is, right? So you want to remember that is the change in kinetic energy, and in general, kinetic energy is equal to a half mv squared, right? So I'll just keep these in the final notes for you guys, and this correction here where I forgot the mass. Okay, so we now have this work energy theorem and a few surrounding facts with the work energy theorem. But so what? What does that let us do? We're going to take a look at 4 examples here. I'm going to try to go through them kind of quickly, so this video is not super long, but we'll plow along through them. I have some of the numbers I'll need calculated here, so I'll pull up my notes. And so our first question is, suppose we have a 30 kilogram package rolling on a conveyor system at 5 meters per second. What is its kinetic energy? Well, this one's pretty easy. We just go to the definition of kinetic energy, and we just said what that was, so that's a half mv squared. And right away, well, we know that we have an m of 30 kilograms and a v of 0.5 meters per second, right? And so, well, right away we can write down sort of what our answer is going to be. Kinetic energy is going to be 1/2, well, m is 30, and v is 0.5, and we need that squared. So if you do the calculation, and I have done it over here, you end up with 3.75 joules, okay? So we have 3.75 joules of kinetic energy in this package as it's rolling on this conveyor system, okay? Let's take a look at a second example, okay? Suppose now that we push a 30 kilogram package with a constant 120 Newton force through a distance of 0.8 meters, and there's an opposing constant friction of 5 newtons. Okay, so let me draw this before we before we get into the sort of questions of what we're going to answer. And I think this one's a little longer, so maybe I will split this page up so I have more room to work with. Okay, so I'm going to start by drawing it, as I said. So imagine this is our conveyor system. We have our box. This is a box, mass equals 30 kilograms. We're applying a force to it, and our force is equal to this is our applied force, is equal to 120 newtons, and we have some force of friction totaling 5 newtons opposing our motion. And we want to calculate, so in A, we want to calculate the net work done on the package. And again, I have these numbers here, so I don't have to pull out a calculator. So let's start off here. Okay, so what do we want to do first? Well, we want to find what the net force is, right? Because we can find the net work done. We know we can find the net work done from this expression. Right? But we want, and I should probably put in our displacement here. This is going to be our displacement, and we're not told what the oh no, we are told, right? Oh yeah, we're told a distance of 8 meters, right? Or 0.8 meters. Okay, so we have our displacement of 0.8 meters. So let me scroll down a little bit. We want to find what the net work done on this thing is, and this is the equation here that we would use to do that. Except that we don't know what F net is yet. We know what each individual force is. We know there's an applied force of 120 newtons pointing in the direction of displacement, and a frictional force of 5 newtons pointing against our direction of displacement. So let's find what the net force is. Okay, so force net, and this is all happening in the horizontal direction, right? So force net is going to be equal to F minus lowercase f, which is just going to be 120 minus 5, which is equal to 115 newtons. And so now we have a value for our net force, and so we can just go straight ahead and calculate the net work done on this thing. So that's going to be 115 newtons times 0.8 meters. And what's the angle between our net force and our displacement? Well, that's 0 degrees, right? So that's just the cos of 0 degrees. And our cosine of 0 is just going to end up giving us 1. And so if we put that into a calculator, we're going to find that the net work done is equal to 92 joules. Okay. And on this other side here, I'll do part B. So in part B, what are we asking for? We want to calculate the work done by each force and then add them up. Okay, so this kind of brings us back to one of the first points I brought up in the video here, that we can look at the work, oops, that's not what I'm looking for, that we can look at the work done by each individual force, or we can look at the work done by the net force and get the total work done on the object. So what we should find is if we add up the work done by each individual force, we should find that it adds up to the total work done on this object. Let's see if that's what we end up finding. Okay, so let's start off by calculating the work done by the applied force. So what we call F here, we're just going to call the work done by that W, and that's going to be equal to FD cos theta. Well, W is going to be equal to, well, the applied force is 120 newtons, and our displacement is 0.8 meters, and the cosine of the angle, well, the angle between them is 0 degrees, right? Our F points in the same direction as our D, and so there's no angle between them. And if we do this calculation, we're going to find that W is actually equal to, I have it over here, 96 joules. Okay, so that's one of the forces. That's the work done on this object by our applied force. let's now take a look at the work done on this object by the force of friction, which I'm going to label that way, and that's going to be equal to the magnitude of our force of friction, the distance of our displacement, and the angle between them. And so what is that going to be? Well, first of all, what's the angle between them? The angle between them is 180 degrees, right? Because our force of friction points this way, but our displacement points that way. And so we have an angle of 180 degrees. If we input that in here, or maybe I'll write out a second step here, we're going to end up with 5 newtons times 0.8 meters times the cosine of 180 degrees. But this is just minus 1. And so this ends up giving us minus 5 times 0.8. And so we find that the work done by the force of friction here is a negative amount of work. And that's fine. We expect that here. And we're going to find that that's minus 4 joules of work done by the force of friction here. If we add these up, we know that the net work done is simply going to be the total of all the works done by all the forces applied to the system, which is going to be W plus WF, and that's just going to be 96 plus minus 4, which gives us 92 joules. And again, that's exactly what we found in part A, and that's exactly what we expect, right? Okay, a third example. Again, I have some numbers here. Okay, so suppose again that we have our 30 kilogram package from the last example on this conveyor, and it has a constant force of friction, as it did in the last one, of 5 newtons opposing its motion. But now we assume that it has an initial velocity of 0.5 meters per second. What is the package's final velocity if the net work done on the package is 92 joules? Okay, so how are we going to get at this one? Well, first of all, we don't really need all this information. We're going to find that this friction of 5 newtons is a little bit of a red herring, because we already have the net work done on this thing at 92 joules. So we don't need to worry about that friction. It's already figured into the 92 joules, as we saw in the last example. So what do we want to do? We want to find what the package's final velocity is. Well, the work energy theorem tells us that if we know the net work done on this thing, well, then this is just going to be equal to the package's final kinetic energy minus the package's initial kinetic energy, right? And we are told what we know what its mass is. Well, okay, maybe I'll just write these over here. So we know that the mass is equal to 30 kilograms. We know that the initial velocity, we're told that the initial velocity is 0.5 meters per second. And we want to know what the final velocity is, right? And that's the final velocity. That's supposed to be a question mark. So we're already in a very good position here to figure out what this is, right? I should probably also mention that we know that the net work done on this thing is 92 joules. And so right away we can just substitute in numbers and basically get to this. But first, maybe I'll clean this up a little bit first. We really want to end up isolating our velocity here. So let's start off by doing that. So let's shift that term so that it's by itself. We have a half mv squared. This is going to be equal to how are we doing this here? We're going to shift, we'll shift that to the other side. So we're going to end up with W net plus 1/2 mv0 squared. And again, we want to isolate v, so let's multiply by 2 and divide by m, right? So we're going to end up with v squared is equal to 2 over m W net plus, and we're multiplying by 2 and dividing by m, so we're going to end up with v squared over here. And then just take the square root of the whole thing here. So we're going to end up with v equals to plus or minus is equal to plus or minus 2 over m W net plus v0 squared. And again, the plus or minus because we're taking the square root of both sides. we're going to select the positive because this thing is going to be going in the positive direction, right? We're pushing it in the positive horizontal direction, and so we're going to substitute in numbers. If we substitute in all these numbers over here, and I won't do it right now, we're going to end up with with a velocity equal to 2.53 meters per second. Okay, and so that's the final velocity that we find if this thing has 92 joules of net work done on it with an initial velocity of 0.5 meters per second. And now let's do a final fourth example here. We're still working with that same box, the same package as in the previous example, and we want to know how far this package coasts after we're finished pushing it if the friction remains, right? So we want to see how far this thing is going to go if the friction remains, okay? So we know that the friction is going to do negative work on this package. So it's basically bleeding kinetic energy out of the system. It's trying to slow this whole thing down. Okay, and so let's take a look at the work done by friction here. So let's write down the work done by friction. We know that this is going to be equal to our force of friction. We're going to call this new displacement d prime, and this d prime is just going to be the coast distance. So the distance that this thing coasts after we finish pushing it, right? And then we have the cosine of theta here, and theta here is going to be 180 degrees. We know that our displacement is going to be in the exact opposite direction of our friction, and if that's the case, then this is going to give us a minus, right? Like the cos of 180 degrees gives us a -1, so this is going to be equal to minus fd prime, okay? And we also know what the kinetic energy of this this object is, right? So let's take a look at that, okay? Let me just pull out my notes here because I haven't calculated the number. Yeah, here we have it. Okay. So what is, well, let's start off by looking at what is the total kinetic energy of the package. Well, we know that the total kinetic energy of the package is going to be given by 1/2 mv squared. And if we substitute in the numbers from above, we know that our m is 30 and our v, well, we just calculated our v in the previous problem. And if we do this calculation, we're going to find that the total kinetic energy at the moment we stop pushing this thing is going to be 96 joules, and this is not a surprise because that's what we found. That the energy that we applied to it, that the work done on it, I should say, in part in our first example was, or I believe it was our second example here. And so what do we have? What do we have going on here? Well, we know that the total work done on this thing had to be 96 joules. So maybe I'll rewrite it a little bit differently. Let's do it like this. Okay, so 96 joules is the total work done on this thing, but we know that the work done by friction now has to rob this full amount of 96 joules so that we end up down at 0 joules of energy when this thing stops. So we know we need to do negative 96 joules of work on this thing, and that has to all be done by the force of friction. And we know that the work done by friction is going to be equal to minus fd prime from this expression up here. Okay? And because of that, we can generate this expression here. And at this point, there's not a whole lot left to do. We know that the magnitude of f is just 5. And so we have d prime is equal to minus 96 over minus 5. And if we do that calculation, we're going to find that d prime equals 19.2 meters. And so what have we found here? we found that the distance that this thing is going to coast. So we push this thing. We do a total of 96 joules of work on this thing. So 4 joules to overcome the friction while we're pushing, and then 92 joules of energy are stored in kinetic energy in this thing, and then we're going to have this 96 joules of kinetic energy bled off this thing by friction, and this gives us the total distance that we are going to that we're going to have this thing travel as it coasts. And actually, I've just noticed that I've written down the wrong number here. Unfortunately, this 96 should not be a 96. This should be a 92, because 4 of those joules were lost in friction as we were pushing this thing. So this should really be a 92, and this should really be a 92. And that may slightly change. This value here. Maybe I'll pull it up on a calculator really quick. 92 divided by 5 is going to give us, so that's going to be 18.4. Right, so let me just quickly restate what I was saying there. So what's happening here? We push this box, we do our applied force does a total of 96 joules of work on this thing. 4 of those joules are lost to friction as we're pushing this thing. We then let this thing go. It has 92 joules of kinetic energy stored in it, and it then slows down over the next 18.4 meters until the point where it comes to a stop, and we found that actual distance that it's going to come to a stop in is 18.4 meters. All right, we'll pick this up again in the next one.